4:30, so let's get started. Our next lecturer will be Cindi from NIST, and she's going to talk about functional magnetic nanostructures because I haven't seen your slides. Have you uploaded yet? Yeah, so I'll just let you go ahead.
Yes, so we're going to take a bit of a digression from spintronics because I kind of got the liberty of going through and talking about functional magnetic nanostructures, which pretty much encompasses most of the field of magnetism, as I hope that I'll be able to convince you a little bit. Please do feel free to interrupt and ask questions at any point. Different sections are more or less independent of each other. And for those of you, if I don't cover your topic, please do not be offended. I did very deliberately choose not to include spintronics. So there's a tiny little bit of spintronics in there, which you'll see, but it's a fairly deliberate effort because I thought you would have seen quite a bit of that already. So what do I mean when I talk about functional magnetic nanostructure? So if we break this down into its component parts, the magnetic part's pretty easy. It's everything, because everything's magnetic. But in practice, I'm not generally talking about diamagnets. We very rarely use diamagnets for things. We generally focus on our ferromagnets, our antiferromagnets, and our paramagnets. Those will also come into play. So what do I mean by functional? Well, functional means it's got to do something. It's not allowed just to sit on the shelf and look pretty. It's got to actually have a purpose. And then the final piece is a nanostructure. And so the ISO definition, the International Standards Organization definition for a nanostructure means that I have to have one dimension that is less than 100 nanometers. Well, that covers a multitude of sins. So I'm going to ask a question. Can anybody give me an example of a nanostructure that meets the requirement of one dimension is less than 100 nanometers? And I will pick on people if nobody raises their hand. And I'm going to pick on you because you've been asking a lot of questions.
An MTJ, I guess?
Yes,
Yeah.
an MTJ is a very good example. It's actually less than 100 nanometers in all three dimensions, but some of the original ones are certainly more macroscopic. Any others? Yes?
Just any magnetic layer in the direction? Less than 100 nanometers?
Yeah, you can have a pretty big thin film as long as the thickness is less than 100 nanometers, and there's lots of things you can do with it. One other example, because I've seen a number of posters on using this particular word. On you. And I know you can say it because you were talking about it.
Thin film can be a nanowire.
A nanowire would be a good example. I was actually looking at you. A nanoparticle. Yep. So here are some examples of what can be classified as a nanostructured material. So we have our MTJ structure. So this is inside a read-write head. But this is also a nanostructured material. This is actually a soft magnet. And it is processed and engineered so that the grain structure inside of it is on the nanoscale. You want something less than about 20 nanometers. You then also can have a nanoparticle system, which is going to be less than 100 nanometers. And then finally, you can go down all the way to the atomic scale. And so a lot of the recent work in hard magnets is looking at actually placing atoms where you want them within a crystal lattice. So these are the topics I'm going to cover. So magnetoelectrics, bioassays, magnetophoresis, magnetic nanofluid hyperthermia, magnetic particle imaging, and nanostructured magnets. I'm going to give you a challenge because it's late in the day. I want to make sure you're paying attention. So I have two common themes. I'll tell you one of them, which is temperature. There's another one that you're going to see throughout this. And the other thing that I want you to think about is I want you to think about how these topics interrelate with each other, because they do. And I'm deliberately not going to tell you the details because I would like this to be a little bit of a discussion point at the end. Okay? So with that, I will start with magnetoelectric devices. So in order to understand a magnetoelectric device, you need to understand what piezoelectricity is. And basically, it's a material that has a lack of a center to your crystal symmetry, such that when you stretch it, you create a polarization. So if this is actually the particular structure, this is a hexagon. If I stretch it along this direction, you can see I'm going to induce a polarization because I have now separated the different kinds of charges. On contrast, if I take it and I stretch it off not one atom but off of one of the axes, you can see that I do not induce a polarization in this material. So this would be a piezoelectric. There is a subclass of piezoelectricity called ferroelectrics. And a ferroelectric is called that not because it has iron in it, but because like ferromagnetism, it has a memory. And so just like in magnetism, you have a hysteresis loop, but now you have polarization versus E field. And so you trace out a hysteresis loop, you have domain formation with different polarization orientations, and you also have a temperature dependence. So this particular temperature dependence is for a common material, ferroelectric material called barium titanate. And this is the dielectric constant as a function of temperature. And you get changes in the crystal structure from rhombohedral to orthorhombic to tetragonal. And then in analogy with ferromagnetism, you hit a Curie temperature, at which point your structure changes to a cubic structure, and you go back to a center of symmetry and you lose your ferroelectricity. So probably the most famous class of ferroelectrics are your perovskites, of which bismuth ferrite is the best one. It has the largest polarization along its pseudocubic 111, which is around the order of 90 to 95 microcuries per centimeter squared. So this is great, but how do you make a practical ferroelectric? And the way you do that, because most of the materials that we make are polycrystalline, is you end up with something that looks like this. And so your crystallographic axes are pointing in all sorts of different directions, and if you actually try and measure a piezoelectric effect on this material, it averages out, and so you get nothing. So one of the very important processes in any ferroelectric material is something called poling. And this basically means you have to apply a very large electromagnetic field at a fixed temperature. All of these depend on the particular material you're working with. And that causes alignment of the crystallographic axes. When you do this, you are now able to recover the piezoelectricity for the sample. One thing I want to point out that's often, because it's a term often used in this literature, is it's generally viewed as desirable to have what's called a morphotrophic phase boundary. And basically what this is this is a coexistence of, at the same temperature, of at least two crystal symmetries. And the idea behind this is the more crystal symmetries you have, the more polarization axes you're going to have. And so that this will overall improve the piezoelectricity of your system. Okay? But one of the interesting things with these practical ferroelectrics is that you can combine them with other effects. So you could have your ferromagnetism, or you could have your ferroelastics. Again, ferro in this case just means memory. And this generates a field that's called multiferroics. And so you may have seen this kind of diagram before. You have electricity, you have your magnetic field, you have your stress and your strain, corresponds to your elastic modulus, your magnetization, your polarization. The problem with most single crystal multiferroic systems is that for ferromagnetism, you want a partially filled D shell. But for your ferroelectricity, you want empty D shells. So you immediately have a contradiction that has set up. And the result of that is that for single-phase materials, you generally have a weak magnetoelastical coupling, and you also have a problem in that they have a very low Curie temperature. So how do we get around this? Well, if you think about a lot of what we've seen on the spintronic side, we can make an artificial magnetoelectric. And the way we do this is we combine a very highly magnetostricted material with a piezoelectric. So as a reminder, for your magnetostriction, basically what you're doing is you are aligning your different orbitals. That changes the length of the material. So this would be your yield-induced magnetostriction. Common material that's used here is terphenol D, which is a terbium dysprosium iron-based alloy. Common piezoelectric you'll see a lot in the literature is your lead zirconium titanates, or PZT. And when you do this, the very first work actually just made discs. And so you have PZT sandwiched on either side with a terphenol. You apply a magnetic field. You're going to decrease the dimension along this axis, increase it in this direction as a correspondence, and that means you're applying a strain to your PZT. And so if you then look at the magnetoelastic coupling, what you see as a function of field and thickness is that you get the largest value of this coupling for your thinnest layer. And so in this initial work, you were dealing with something that was pretty small, something on the order of millimeters. But the smaller you go, typically the better off you get. And so the next phase was taking your disc and turning it into a ring. And when you turn it into a ring, you're able to concentrate all of the deformations along the outside edge, and that gives you an enhanced signal from the material. This particular one had a sensitivity of about 1 nanotesla. Current work has something on the order of sub-picotesla. So they have very good magnetic field sensors from these materials. But what kind of parameters are you controlling when you're trying to design these? So for the materials, you want a very large magnetostriction. The bigger it is, the more strain you can apply to your system. You then want a large, what's called pyromagnetic ratio, which is the change in the magnetostriction of field. You want a large permeability, a large magnetic anisotropy, and this is sometimes called piezoelectric coupling coefficient and sometimes called magnetoelastic coupling coefficient. And then the geometry matters. What's the volume fraction of the different layers, and what kind of configurations do you have? So this is another generation, more recent one. This is focused more on the flexible side of things. So we have a mica layer in here in order to add to the flexibility. Sensitivity here is about 0.2 nanotesla. But one thing you have to pay attention to in these materials is that although I say that's the sensitivity, the limit of detection is only about 200 nanotesla in this case. So that's one of the things that you really have to pay attention to in these materials. In addition to making magnetic field sensors, you can also make antennae with these materials. You can make them operate in the very low frequency and the very high frequency. And if you make an antenna, you can then make an energy harvester. And so the idea behind the energy harvester is you want to translate electromagnetic waves, our vibrations, into electrical energy. And so the idea is that in this structure, it's working in out of plane. So the thickness is what matters, and these thicknesses are quite thin. They're on the order of hundreds of nanometers. And this is what's called a dual band, because one of the limitations of these is they're tuned to work for a specific frequency range. So you can see one band is operating in this frequency range, another band is operating here. By combining them, you're able to enhance the absorption over a much broader range. And then one of the nice things with these is that they have a much better power transmission efficiency than any coils that you can make. And they're pretty insensitive to offsets and angle variations in them. And the improvement is 1 to 2 orders of magnitude currently. So it's not a small variation. Questions? So the next topic is on bioassays. I did warn you there was going to be a tiny little bit of spintronics, and that's because this uses both magnetic nano objects and also MR sensors. So what do I mean when I talk about a bioassay? So a bioassay's purpose is to detect something biological. This can be something as simple as taking a pregnancy test, which is a particular class of bioassay. It can be a test to see, have you been vaccinated for a particular material because you're looking for the antibodies? Do you have a particular pathogen in food and therefore we need to recall this product? You're looking for the signature of something. And there are many ways of doing these kinds of assays that already exist. The most common one is cell culture. Basically, you take a swab of whatever it is you're looking at it, you put it on cell growth media, you put it in a petri dish, put it in an incubator, come back a couple days later. It takes a while to do because what you're looking for is visible colonies of cells. So you've got to give time to the cells to actually grow and multiply so that they become visible. There's an intrinsic problem with this. If you're trying to grow bacteria that are anaerobic, you put them on a petri dish and there they die. Doesn't mean they're not there, just means that you can't see them. And so this is a really big problem if anybody's ever had a bacterial infection and you can't culture it, because then you're making wild guesses about what kind of antibiotics to use to treat it. Other cultures, or other methods, are polymerase chain reaction, PCR, and enzyme-linked immunosorbent assays, or ELISA. If you really want to know the details of them, I'm happy to explain them. I'm not going to go into it here. The nice thing about these is that they have incredible selectivity, and you can go through and identify very specific parts of the genetic code, but they're expensive, they're time-consuming, and they require skilled labor to be able to be done properly, and they are subject to false positives. So, one of the things that we're looking at is going into doing different kinds of sensors. So this is just kind of a summary of what was before. Other sensors, types of sensors that are being used are optical, electrochemical, and mechanical. They all have pros and cons, but this is where my spintronics comes in. I'm going to use GMR. Right? So you've already seen this. You have the two current models, parallel, low resistance, anti-parallel, high resistance state, and how that actually matters is because we're going to use the magnetic nanoparticle in order to change the field that they see and therefore the orientation. So if this is my GMR sensor, the first thing I have to do is put a passivation layer on it. And the reason is you're sticking these in water. You don't want to oxidize your magnetic fields. Then you have to attach something to the surface. And so if you think back to a children's toy where you have a round hole, a square hole, and a triangular hole, and you have a round peg, a square peg, and a triangular peg, and you have to put them in. The basic idea here is that you put something that is identified according to what it is you're looking for. So if you're looking for an object that is round, then you put on something that is round. The technical terms for these are your antibodies, which you've probably heard, and antigens, which is what they stick to. And so you conjugate the surface down here, and then if you have another nanoparticle, it'll come in and attach. That's going to change the magnetization angle here, and so you're able to shift the MR. The nice thing about this is that it makes it a very quantitative measure. The difficulty is how do you go about and do the surface modification? So the aptase glue is a very common method. It starts with hydroxide. You basically attach silicon to it through silaning. Then you put an aldehyde group on the end because you want the amine group, and then that's how you do everything else. But the basic process is you've got something down here. So this would be, for example, if you're looking for an antibody, this would be your antigen. And then your antibody shows up here and sticks to it. And then you have the other half of that will come and stick to this side of it. And then your nanoparticle will come along and stick to it here. This requires that you do a lot of washing because you don't want nanoparticles that aren't bound to anything. So a wash-free method is basically you mix it all up beforehand so the nanoparticles are already attached here. And then the only thing that happens is that you wash it once and what's left is what's stuck. If you have something that you're looking for that's very small, you do what's called a competitive assay, where basically you mix it, you pre-bind everything, and then what's pre-bound will go away, what's left will actually bind, and so you're measuring the inverse of what you're actually looking for. So you're looking for a signal decrease. Just to prove to you that it works, this is what's called a multiplex bioassay. So you have different regions which are conjugated looking for different things. And you can see as a function of time, you can get pretty significant detection levels. And so the time scale on here is only about 30 minutes, so it's actually quite fast. Another thing you can use it for is something called circulating tumor DNA. So if you have cancer and you're going through treatment for it, one of the things that they want to look for a while afterwards is they want to look for recurrence of it. And the way they do this is they look to see if any of the tumor cells have gotten into your bloodstream. But you're looking for 1 or 2. You're not waiting to see millions. And the reason why you're concerned about the circulating tumor cells in large part is because when they start shedding and moving into the bloodstream, they can go somewhere else and form another tumor. And that gives you metastatic cancer, which becomes incredibly difficult to treat. And so this is a form of the MR bioassays. And so you can see that you're not seeing it in the tumor growth early on, but after about a month you get enough signal that you can actually, you can see this, and so you can again see this is the control sample, and you well above the threshold in this case. This particular one used a method of amplification, which is based off of PCR, but it is localized on the surface of the magnetic nanoparticles themselves. But one of the interesting things is that although this is using PCR on a magnetic nanoparticle, you use a magnetic field in order to concentrate the nanoparticles down towards the sensor. Because the sensor in this case is not an MR sensor, it's an electrochemical sensor. And the end result of that is you get cooperative phenomena in here that enables charge transfer, and it gives you amplification of the signal. And so you can get attomolar limits of detection on these materials, which is really, really quite incredible. That piece. Questions? Yes?
I don't really know about bioassays, but with those nanoparticles, you kind of already need to guess what kind of bacteria or whatever you're going to study, or...
You have to know what you're looking for. This isn't something where you just go, oh, I just want to see what else in the bloodstream. You're doing a test for something specific.
But some other techniques you could go like, we don't know what we're looking for.
No, none of the assays. They're all specific. The exception to that is the cell culture, because you're not doing an identification. It's just, do I have bacteria growing? And then you might use optical microscopy to see if you can identify it, or then you might go and do PCR or ELISA or something to identify the specific pathogen. It's not a fishing expedition. It's targeted. Yes?
Is there a reason you use GMR stacks as opposed to TMR stacks?
The reason is because you want an MR that will change with small changes in the alignment of the layers. And TMR is, because of the resistivity, is not going to give you that. And part of it is also just historical, in that this is just part of GMR sensors that were existing because this work started about 20 years ago.
Thank you.
Yes? Oh. It's in the back, sorry.
I have a question regarding the functionalization process. Do you think that your passivation layer, do you think that the passivation layer you make will be able to be functionalized with everything, or do you think you'll have to change the passivation layer depending on what your aptamer or whatever you're binding to that surface would be?
Silica is a common one. Gold is another common one, because the chemistry there is well established. You use silane groups for the first, and you use thiol groups for the second. And as long as you can put a thiol group or a silane group on the end of it, then you can attach. And the other end is free to do whatever else you want with it.
Okay, so you think you could make multi-step chips that would be, maybe you could detect multiple things on the same chip, if it would be possible to fab it.
That is the multiplexed one, but it's not that you're putting 3 different antigens right next to each other. You have one region for one antigen, another region for a different one. So they're, the processing is each individual, and then you put them together.
Okay, thank you.
So the next section is magnetophoresis. So what do I mean by magnetophoresis? Fundamentally, it is just a magnetic field-induced motion in a binary phase, which is a really fancy way of saying you've got magnetic nanoparticles in water, or any other liquid that you fancy. The forces that you have acting on it, on your particle, is you have gravity pulling it down, you have buoyancy pulling it up. Buoyancy is actually rarely considered when you look at the equations. You have your magnetic force, and you have your drag force. So gravity we're all familiar with. Drag is proportional to your viscosity, your velocity, and the effective diameter. So whatever your particle is, you assume it's a sphere of the same volume, and then that's what that diameter is. Your magnetic force is, of course, your moment times the gradient of your magnetic field. But then there's another piece of it, which is you'll also have your torque. So this force is what will translate it. But this torque, which is the magnetization across the magnetic field, is what's going to enable rotation. And both of those come into play. So the size range that you're working at really depends on where your magnetic force is going to dominate. So at some point you get large enough, gravity's just going to pull it out. And it's somewhere in this middle range where you can go up to about 1 millimeter in practice. Typically you're on the order of a micron or smaller in these materials. And when you do this, there are some different examples of how you might do it. So the first one, you have your magnetic bead, you have your magnet with your magnetic field gradient, and it just moves it. Another example is you have a magnetic head and you have some sort of tail on it. You apply a rotating magnetic field. That will actually spin the tail, and then that will give you translation. You can combine a magnetic field gradient and a rotating magnetic field, and you can get zigzag chains or just straight chains to actually rotate and move in different directions. So how do people design magnetophoretic objects? These are often termed magnetic robots. And the obvious place to start is you look at biology. And so you look at different kinds of cells and different kinds of things that move. And so you can have straight tails, you can have curved tails, and they can do different kinds of spirals. And then they can have something that's more long and slender and just kind of wavy, or it can be kind of stumpy. The question is, how do you make something like that? And without going into a lot of the detail, it's actually really complicated to do this. It's highly non-trivial because you're trying to work starting with some sort of 2D material and then turn that into a 3D object. But there are ways you can do that. You can do that with folding. You can do that with basically cutting along particular axes, which then will cause things naturally to want to curl up. And so in doing that, we can form different designs. So this is one where you've got a tube that curled up, and now we have a tail that's curled along on the outside of it. And if we look at what happens on this, so this is that structure, and you can see here, this is a time-elapsed image. It's going up, and it's moving. So you've got the massive head, and then the tail is moving up and down and propelling it in the forward direction. And that's kind of what's going on theoretically here from simulations. But turns out that there's a simpler way to produce this kind of robot. And that is to use a nanowire. And one of the properties in nanowires is that they have very strong shape anisotropes. And so if you control the length of the magnetic material, so in this case it's nickel, and you have a very long axis, shape anisotropy is going to want to lie parallel to the rod. If it's a very short, basically more of a thin plate rather than a cylinder, then the magnetization is going to want to point out of plane. And the end result of that is when you combine these two and do the vector sum, you get a magnetic moment that is slightly off of that center axis. You can then apply a magnetic field gradient from a permanent magnet, and you can apply a rotating magnetic field from these coils. And what happens when you do that is that axis that it is, the magnetization vector, will line up with the magnetic field from the permanent magnet, and that will enable it to translate. But then because of the fact that this is the physical nanowire is slightly off axis, it will spin, and it acts like a drill. And so, so this is actually a video of one of these, and you can see it kind of walking along and spinning. The reason why this kind of thing is important is because while we might think of the fluid in a cell as being basically water and pretty easy to move through, it's not. There's a cytoskeleton, there's lots of proteins, there's all sorts of junk that's in there. If you think about going through the bloodstream, you've got the same problem as well. And so being able to unstick yourself is something that's very important, and this is a really neat way of unsticking the robot. So you can do things like drug delivery, you can do mechanical destruction of cancer cells, you can do cell stimulation to treat nerve damage from an injury that's causing paralysis. And another example robots here. We can just use an ordinary nanoparticle. But one of the really neat things is looking at how you can use magnetic nanoparticles to clean up water. So what's going on is you start with your magnetic material. You do a lot of chemistry to the surface because basically you want something that's going to pick up the dye you're looking for or a heavy metal. This particular example is for arsenic. And what basically happens is that when you put these into water that contains, as they're floating around, they will actually bump into any arsenic and they will bind to it, assuming that there's no arsenic already present. And then later on, once you've bound, you can apply a magnet to it and use magnetophoresis to pull it out. And so then you can pull the arsenic out, and you can do this in a flow process, not just in a test tube. But one of the neat things is once you remove the arsenic-containing nanoparticles, you can actually desorb the arsenic. And you can remove it, in this case, just by using sodium hydroxide. And when you do that, you can then regenerate and reuse the magnetic nanoparticles. Yes?
So actually, yeah, so in the previous image, you were showing some imaging.
In this one? Yeah, this was just an optical microscope image.
Yes. So here you are applying magnetic field, is it so?
Yes, there are two fields. There's a magnetic field gradient and a rotating magnetic field.
Okay. So this gradient, I mean, like how you are providing this gradient?
The gradient comes from a permanent magnet, just on one side. So, I go back up. So you've got a permanent magnet over here. So you have a nonlinear magnetic field gradient. Your rotating field comes from a set of coils that are along the XY axis.
Okay. So sorry, like I'm not very aware with this field, but I want to know like what is about the reproducibility. I mean, like you are providing some field, and this particular thing is behaving in this way. But is it showing the same behavior again and again?
So the measurements have been done on multiple different nanowires, and they all spin. You can play games with controlling the relative thickness of the different magnetic layers. You can change that angle, and so you can make them look like they're tracing out kind of different kinds of circles, but they're all basically acting as a drill. It's highly repeatable. You change the magnetic field gradient, you're going to change the speed at which it happens. You change the rotation speed, you're going to change the speed at which they rotate. It all becomes controllable.
Yeah, like you were talking about using it in some magnetic robots.
Yes, so this would be a magnetic robot.
I see. Okay. And initially, where there was a title where you used like a magnetic field induced motion in binary phase. So this binary phase is like 1, 0, or is it like?
The binary field is a magnetic nanoparticle in water. So it's the materials.
Okay.
Yeah.
Thank you.
Not binary as in computation.
I see. Okay. Thank you.
Other questions? And so then I mentioned that you can also do kind of continuous flow. So these are examples for biomedical applications where you can do continuous flow in order to remove, again, coming back to it, circulating tumor cells. But you can also do isolation of white blood cells, for example, to look at different aspects of it, to count how many there are in a particular volume of blood. Other questions? So the next one is a topic called magnetic particle imaging. You may have heard of magnetic resonance imaging. I don't know if anybody has ever had an MRI done on them. This is a new imaging modality. It was originally developed for biological applications. But the basic idea behind this is it uses the nonlinear response to the magnetization. So if you have a hysteresis loop for whatever your magnetic nanoobject is, and then you apply an AC magnetic field that's varying with time, it's going to trace out a magnetization as a function of time that looks like that. So this, of course, is time dependent. We can take a Fourier transform, and we're going to end up with a signal. And this is considered a strong signal because we have a lot of amplitude in these higher order harmonics. We have more amplitude in the 1F in your dry frequency, but it contains your dry field. And so nobody ever uses this one in actual MPI simply because it's impossible to remove that dry field. If I now shift our AC magnetic field and I shift it to somewhere closer to saturation, I'm still applying that AC magnetic field, but now the change in the magnetization that's going to be traced out is quite small. So again, I take a Fourier transform of that, and it's going to be a pretty weak signal because I'm not getting very much in terms of these higher order terms. So I can distinguish the signal from a nanoparticle and no nanoparticle as long as I can put it in a field-free region. And so the way they do that, conceptually, I'm going to talk about it as a field-free point. Modern MPIs use a field-free line. But the basic idea is you have a series of coils on either side that are producing very large magnetic field gradients, and then you can tune the current in each one so that you can move this around. Wherever you have a field-free point, that's where you're actually going to see the signal. So one of the things about MPI, it doesn't see biology. So if you want to look at a human being and you want to identify whether you're looking at something, a nanoparticle that's located in the liver or the lungs, you need anatomical information from something like MRI. Okay? So this is an example of a mouse. And so the anatomical information, the skeleton information is coming from MRI, and the information, the bright spots up here, this is the location of the nanoparticles. One of the really nice things about this technique is that it is real-time imaging. So you can actually watch the nanoparticles in the blood as they flow through the heart to look for blockages. And this particular application is of a lot of interest in this field because heart disease and kidney issues come hand in hand. But if you want to do real-time imaging, you're typically doing PET-CT, maybe a little bit of functional MRI, but mostly PET-CT. Functional MRI uses a gadolinium chelate as your contrast agent. PET-CT is going to use a radioactive isotope. None of those are very good for your kidneys. If you have people who already have compromised kidney function and you do one of these tests on them, they're really risking having them end up on permanent dialysis. On the other hand, you stick iron oxide, they eat it every day, whether you're a meat eater or a vegetarian. It is constantly in your diet, your body knows what to do with it. And so it's not a problem, you don't risk compromising kidney function. But where we got really interested in this is we got interested in using this method in order to probe temperature throughout a volume using magnetic fields. So as Elaine mentioned yesterday, if you want to measure temperature, you need a property that has a strong change with temperature. So if you think about the old mercury thermometers, this was a change in density. So what we want is we want a strong change in the magnetization with temperature where we focused around what was going on at room temperature. If you have a paramagnet where your N versus T looks like that, you already have a strong change in the magnetization, but it's down at cryogenic temperatures, which we weren't terribly interested in. So again, the temperature sensing works the same way. You apply an AC magnetic field, different temperature regions, you get the Fourier transform, and then you can look at the harmonics. Primarily, you're going to be looking at ratios of harmonics, so you don't have to worry about how many nanoparticles are in your system. But you can then use that in order to reconstruct your 2D image. And so this is an actual thermomagnetic particle image. So what are some of the design parameters for good thermometers? Well, first thing is you've got to have a good thermosensitivity. You've got to have a good signal. And if you want to do imaging, you've got to have good spatial resolution. And it turns out if you want good spatial resolution, you need to go to the higher order harmonics. But the higher order harmonics always have lower signal, so you've got to trade off in terms of how far out you can go with your signal. And then the question becomes, what kind of thermosensitivity do your higher order harmonics have? So to work on this, we actually were engineering magnetic nano-objects. There were two things we were playing with, the interfacial magnetic coupling and the interparticle magnetic coupling. So we were doing chain formation. And so this basically broke down into composition control, because if we have a Curie temperature here, for example, that gives us a strong change in the magnetization. These multi-layers, so you can change the interlayer coupling and the interactions. One thing I do need to mention is we have to define what we mean by thermosensitivity. It's fine for me to toss out that word, but I need to tell you what it actually is. So we modified the definition that's used for other thermometers for the particular parameter we were measuring.